Good morning, everyone. I wanted to talk about your stoichiometry discussion and kind of put my 2 cents in and help out those of you who are feeling confused. Overall, lots of really great thinking and ideas. I do think some of us were a little lost and some of us were on the right track, but we didn't get fully there, so I thought a good wrap-up video would be helpful. So first of all, we were mixing grams, a certain amount of grams of NaHCO3 with a certain amount of milliliters of HCl. This is a double replacement reaction, so the Na is going to trade places with the H, so that means we'll have NaCl, and then H and H make H2CO3. I put in states of matter. If we're measuring grams of something, that's a solid. If we're measuring milliliters and they give me this big capital M, that means aqueous. I'll talk about that in a second. We know NaCl is going to be aqueous. That's just salt. And so if there's water around, it's going to dissolve. And then I have a question mark here because we don't really know what this thing is. We see obviously a gas is being made, and then we also see some stuff left in the bottom of the flask. So one thing that some of you looked up and were able to figure out was that H2CO3 actually naturally breaks down into H2O liquid and CO2 gas. So if I rewrite this balanced equation, NaHCO3 makes HCl, plus HCl produces NaCl, H2O liquid, and CO2 gas. So let's talk about the NaHCO3. We need to be able to convert from grams to moles, so I found the molar mass of that. 1 Na plus 1 H plus 1 C plus 3 O's gives me the molar mass. And then for HCl, we have this new idea here called 3M. Some of you asked about this, but I didn't remember seeing any post where anyone looked up, maybe one. So what is 3M? Well, M stands for molarity, which is the same thing as concentration, okay? The formula for molarity is capital M equals moles divided by liters. And just a friendly reminder, 1,000 milliliters is 1 liter. So it's kind of like density. It's an amount divided by the volume, right? It's just instead of grams and milliliters, we're using moles and liters. All right, I got a little video about molarity, super short, maybe. All right. Get everything back. Okay, so my thinking is, I know we have 3 molar. Is it possible for me, sorry, I want this whole thing. There we go. Okay, I want this entire thing. We have 3 molar. I want to be able to solve for how many moles, right? We have molarity. I want to know how many moles of the HCl we're adding. So I did some conversion. So in flask number 1, I had 10 grams of NaHCO3, so I'm going from mass island to mole island by dividing by the molar mass. And now for my molarity, well, first molarity is moles per liter, so I'd have to take 25 milliliters and divide it by 1,000 because there's 1,000 milliliters in 1 liter. So I get 0.025 liters. And then I can solve for my missing variable, which is x up here. So 3 molar equals x moles over 0.025. I crisscross multiply, so 3 times 0.025 gives me 0.075 moles of HCl. And I'm going to do that then for each of the flask. So I'm using the numbers that were provided here for flask 1, 2, and 3. So I've turned this guy, notice they're all the same because we had 10 of each. And then now 50 milliliters is 0.05 liters. I solved by crisscross multiplying. Same thing here, solved by crisscross multiplying. So I have different amounts of HCl in each of the flasks, which most of you noticed. So now I'm going to do a BCA table. So for flask number 1, I took the given moles that we just found and the amount of moles of HCl that we just found. We didn't start with any product before mixing. Minus 1x plus 1x because our stoich is 1 to 1 to 1 to 1 to 1. Now I find x. So I'm going to take B divided by 1 right here and B divided by 1 right here. My smaller one is HCl, which means HCl is my superstar, my limiting, and x is going to be that value of 0.075. To find my A box, I take B minus C, or B plus C to get A. So 0.12 minus this guy gives me how much leftover there is. This guy minus this guy is 0. 0 plus 0.075, right? And I have how much was produced. I'm going to do that same process for each table. Really, the only thing that is changing is the amount here. So if you look in flask number 2, my superstar has changed because when I went to find x, 0.12 divided by 1 is smaller than 0.15 divided by 1. So now this guy is my limiting, and it turns out in flask 3, the NaHCO3 is also the limiting. So flask number 1, HCl was limiting, and the other 2 flasks, NaHCO3 was limiting. Some of you noticed that. So now, and this is where I think some of us assumed that flask 1 was automatically, and I know that picture is kind of hard to see. Let's do this. Thank you. Okay, so some of you assume flask 1 was automatically blue, flask 2 was orange, and flask 3 was green, but I want to match them. So here are my observations. Let's start with the blue balloon. There was the most liquid. If we zoom in, there's more liquid here than in the others. There was an odd balloon shape. That was just kind of a weird, I think the balloon got stretched a little bit, but maybe it's the same size as orange, not really sure. Okay, the middle balloon has the middle amount of liquid, so less than this guy, but more than this guy. And maybe the same size balloon here, hard for us to tell. And green had little or no liquid. There was white solid, and the balloon was significantly smaller than the other two. So I tried to match. Well, when we did our BCA table, in number 1, we noticed that there was excess of the NaHCO3, right? Let's look back. For flask number 1, I made product, NaCl, I made water, and I made 0.075 moles of gas. And there's excess of the solid. Which one do you see excess solid in? That's the green balloon, right? Also compare the CO2, 0.075 to 0.12, and then this guy is also down here, 0.12. So these ones made the same amount of CO2, this one made less. Who has less CO2 in the balloon and leftover solid? That is the green balloon. So I said that flask number 1 was probably the green balloon because we had leftover NaHCO3 and we had less CO2 produced. Then the one where we produced the middle amount of liquid in the flask, if you look at your BCA table, this one, look at the liquid or the aqueous things. We have 0.12 water. We have 0.03 of this aqueous HCl left over. Here we have 0.18 aqueous HCl and 0.12. So the water produced is the same in both, but one of them has more leftovers. So I'm going to argue that flask 3 is the one with lots of liquid left in the flask because there's lots of excess of this aqueous HCl. So that's how I got the numbers for 1, 2, and 3. So really this is my 1, flask 2, flask 3, if I'm matching the numbers. Now the last step is particle drawings. Some of us really struggled with this. I know it's been a while since we did particle drawings first semester. Do they have to be as detailed as mine? No, most of them were not, but I'm trying to kind of make a point here. So here's what I did. I assigned each capital letter a symbol. So NA is one capital letter, gets the orange square. You can see orange square. H is the red circle. So anytime there were H's, I drew a red circle. Carbon was the black rectangle, and oxygen was the blue circle. Cl was the green triangle. So I look at my before. Where are these numbers coming from for NaHCO3 and for the HCl? Those numbers are coming from my BCA table. Here's how much we started with before. They're separated because they're not mixed before. In a perfect world, these would have been nice whole numbers, and one little particle could have represented 1 mole. Obviously, I was just kind of doing rough ratios here, so they're not perfectly to scale in terms of is 0.12 represented by 3 particles and 0.075 represented perfectly by 2? No, but again, work with me here, people. So if now we know that every time this reaction happens, we're going to make one of each of these. So this guy plus this guy can make each of these. So if I react this guy with this guy, I can make one of this, one H2O, and one molecule. Okay, so I essentially, let's use my little highlighter. I used up this guy and this guy to make this. Yep. Okay, now I'm going to use this guy reacting with this guy to make this guy, and this guy. Well, what's not crossed off? I have not used this, and so there's my excess. So left over, I have made 0.075 moles of CO2 produced. That was in my after box on the BCA table. I made 0.075 moles of NaCl, 0.075 moles of H2O, and there was leftover in this flask. That's the solid right there. So leftover, I had 0.045 of that solid excess in my after picture. Oh, that's annoying. No more highlighter for me. Sorry for this ghetto video, guys. Okay, second balloon, we had the same, we'll just use this pointer. We had 0.12 always of these guys, so I always start with 3, notice. And now I have more of the HCl, so I added some particles. If we do our reaction, this guy reacts here, we make 1, 2, 3, those guys. This guy reacts with this one. We make another water, another this guy. He reacts with this one. We make the third water and like essentially the third of everything. What's left over? Well, if I react 3 of these, there should be 1 of the HCl in excess. So let's check our BCA table. It said we should make 0.12 moles of CO2, 0.12 moles of NaCl, 0.12 moles of H2O, and there should be excess leftover HCl unreacted. And last but not least, same situation, except now there's even more HCl to start with. So essentially there's even more leftovers, 0.18 moles of HCl in excess. So these drawings are very, very similar. The result is that we just had more of the excess HCl left over, which is why this flask had so much extra liquid in it at the end. I hope that helps clarify the molarity piece and the drawings, but overall, really good job. I'm sorry this ran a little long, but I'm hoping it makes more sense and connects back to the stoichiometry unit.